right, more linked list. Oh wait, I should linked list. Yeah. I think I'll just I skipped this one. Yeah, let's try this one again. Images are stored in reverse order. Each of the nodes add the 2 zeros. Okay, I think yes, yeah. So yesterday tried this problem. Try to just update the longer ones. Not how you should do it. You should create a new linked list. So let's do that. So the strat is dummy equals list node. And if you don't put anything, just default to 0 and text next is equal to none. Create a reference to the dummy head. Oh, let's while L1 and 4 L2 store the values. V1 equals L1 V2 dot val. So we need a carry equals 0 such that we want to add V1 plus V2 plus carry, and then the value is going to be modulo 10. Carry, update the carry if there is a carry. So val divided by 10. Val modular 10. Cur dot next equals this node val, and now we update right, else 0 else 0. So now we need to update L1 L2 L1 equals L1 dot next. They cur too. L2 dot next. Or carry. So this needs to be a condition because, for example, you have the edge case of adding a single digit number while there's a carry. In that case, um, both of these values will be none. However, we still have the carryover. So we run through the iterate carry, and then we end. So after we exit the loop, then we can return dummy.next, which will give us the first node of our list. Oops. Oof. Okay. Else none. None. Okay, think I got. Yeah, I mean, I should start a timer. Give myself 40 minutes. Yeah, 25 minutes. 2 add 2 numbers. We try second time. Okay. I think this one's pretty chill. Yeah, I've done this one before. Let's try it again. Yeah, so there's a formula for this. Equals head. So the fast pointer will go 2. I actually don't know. Is there a difference between Ah, yes. So it is different. So let me fix this. This. Nice. Yeah. Let's see what happens if I try to do it that way. What? Nani? How come this works then? Okay, I'm not sure. I'll have to double check on that. Find the duplicate number. Okay. Given the array of numbers in integers nums containing n plus 1 integers, given the array of numbers wait, what? Is this even the right question? Without modifying the array. Oh wait, what? This is a linked list problem? Okay, wait. Let's watch it. Maybe I'll be able to solve it.
Alright, this is what I've been training for. I'm not gonna let Senpai down. What do we have here? Find duplicate number. Given an array nums containing n plus 1 integers, where each integer is between 1 and n inclusive, prove that at least one duplicate number must exist. Of course, because of the pigeonhole principle. Child's play. Assume that there is only one duplicate number, but it could be repeated more than once. Find the duplicate number. I got it. If the numbers are sorted, then any duplicate numbers will be adjacent in the sorted array. A simple sort and a linear scan will do. As expected, I knew it couldn't be that easy. But if you think that would stop me, then you underestimated me. I have no choice but to use my secret weapon. Hash map. The famous hash map, one of the most powerful data structures for reducing your time complexity, taking advantage of its constant lookup times. However, using a hash map requires me to increase my power level, so I need to wear these to suppress and control my powers in case it gets out of control. Also, my doctor told me to wear them to treat my carpal tunnel. Honey. Wait.
This question is too strong. I'm too weak. I'm running out of ideas. I can't solve this meme problem. How can I even be a real engineer? How am I gonna get into Google?
Seems like we need some help.
What?
This question is trivial.
Oh my god, he's so cool. And his jacket is so big.
Solving this in linear time and constant space requires Floyd's tortoise and hare, a simple cycle detection algorithm where one pointer traverses twice as fast as another, and once they meet, you can trace back to the point where the cycle began. In our case, the values of the array is like a pointer, pointing to indices of the array, which is like nodes in our case. Because each number is from 1 to n, then each value will have to point to a valid index, and since there's a duplicate number, there will be a cycle. Find that cycle, and you will have your answer. What are you waiting for? Code it yourself. Senior engineers don't code anymore. Also, my doctor said not to, because of my carpal tunnel.
Nums of hair. What the fuck?
That works. Senpai, why are you so smart?
Holy.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve find the duplicate number. And you can see that I'm not really a big fan of this problem, and maybe I'm just salty, but I really feel like this type of problem is the ultimate test of whether you've seen the problem or not. But I'm still solving it nonetheless because it's an interesting problem, and it does show up in interviews quite a lot, it seems. I really don't know how anyone would be able to solve this problem in a 30-minute interview without having seen it. Even the person who came up with the algorithm, Floyd, I doubt even he could solve this in 30 minutes in an interview setting. But that's okay, let's just learn the problem today. So we're given an integer array of nums containing n plus 1 integers. This is the length of the array, but every single value in the array is going to be within the range 1 through n. So we have n different values that could be in the array, like n different choices for the integers, but we have n plus 1 integers. So that kind of implies that at least one of the numbers is going to be repeated, and they tell us that actually it's only one number is guaranteed to be repeated. And the only thing we want to do is return the number that is repeated more than once. Now, the easy way to solve this problem, of course, would just be have a hash set, right? Iterate through every single value, find the one that occurs twice by using our hash set. That's going to be O of n time and O of n memory, but they tell us that we can only use constant extra space, and we can't even modify the input array, so we can't even sort it or anything. And I think those restrictions probably make this a hard problem rather than a medium problem, but that's okay. So there's two aspects to this problem, and I'm going to explain both of them. So we're going to solve this in O of n time and O of 1 space. The first thing to recognize is this is a linked list problem, specifically a linked list cycle problem. And the second thing is to know Floyd's algorithm, which will tell you the beginning of a cycle in a linked list. So there's two problems: one, to even recognize that this is a linked list problem, and two, to know the algorithm to actually apply to it once you know that. So let me actually show you how we can figure out both of these things. And yeah, you're right, it's probably not super intuitive, and I'm not really sure how you would be able to figure it out on your own if you've never done something like this before.
Bro.
So remember that the length of our array is n plus 1, but every value in the array is going to be between 1 and n. So there's n different values, but there's n plus 1 positions. So in this array, we have 5 different elements, right? And we know that the elements are going to be in the range 1 through 4, right? So basically, if instead of thinking of these as values, let's think of them as pointers. So we know for sure that every single value in the array is going to be in the range 1 through 4. That means if we considered every value as a pointer, each value is going to point at some position in this block of 4. You can see that this one points at position 1, this 3 points at position 3, this 2 points at position 2 over here, and this 4 points at position 4 over here, and then this 2 points back at position 4. So that's how you can kind of see that, you know, in that case there was a cycle, and you can see I basically drew out the linked list version of that. So it's not hard to see that this portion is going to form a cycle, because no matter what value we look at, it's going to point at some other value inside of this range. There's never going to be an exit condition. None of these values are going to point outside of the range, either, you know, over here or over here. None of them are going to point outside of the range. So this portion is going to form a cycle linked list somewhere, right? What about this value? Is this going to be a part of the cycle? Notice how none of these values, nothing is ever going to point at index 0, because remember, our range is between 1 through 4. None of them is going to be 0, so none of them is going to point here. So we can guarantee that this is not going to be a part of the cycle. And when you see, I took this array, drew it as a linked list, you can see this is index 0, right? You can see that this was our cycle portion, but this was not included in the cycle. And that's going to be very important because when we start traversing this linked list, we're always going to start here because we know this is not a part of the cycle. So in our input array, you can see that 2 is the duplicate, right? 2 is the one that shows up multiple times. So in the context of this problem, this position is going to point at index 2, and this position is going to also point at index 2. So what does that tell us about our linked list? That means at the node that's labeled 2, each value of the node, each label is going to map to the index. So this is basically node 2, right? What that tells us about node 2 is that multiple nodes are going to be pointing to node 2, right? Therefore, we
3 is, wait,
know that this is the one that's going to.
so index 3 is pointing at 2, 4 is pointing at 2, 2 is pointing at
be the start of the cycle. We know for sure there's going to be a cycle, and we know for sure there's going to be a portion before the cycle. The portion before the cycle, of course, is eventually going to lead us to here, which is the start of the cycle. And of course, there's going to be another node that completes the cycle, right? Pointing back to this node. So if we can somehow identify the beginning of a cycle in this linked list, then we will know that that beginning of the cycle is the return value that we're looking for in the output. You can see, yes, 2 is the duplicate. That's the one we want to return. Therefore, we want to return the start of the cycle. So at this point, it's all about applying Floyd's algorithm to find the beginning of a cycle. So that's, once you've determined that it's a linked list problem, then you just need to apply this algorithm, and this algorithm itself is actually also not very intuitive. So let's look at a slightly different example so I can illustrate the Floyd's algorithm. So first I'm just going to tell you what the algorithm is, and then I'm going to explain a little bit of the intuition of why it actually works. So the slow pointer and fast pointer are both going to start at this position. The slow pointer, of course, is going to be shifted by 1 each iteration. So that's 1 jump, that's 2 jumps, that's 3 jumps. So we just made 3 jumps with our slow pointer. Let's do the exact same thing with our fast pointer. So remember, a jump with the fast pointer is going to be 2 positions. So that's 1 jump, that's 2 jumps. And let's make 2 more jumps from here. So we're going to go to 2 and then back to 3. So you can see that it got a little bit messy, but we made 3 jumps with the fast pointer and we made 3 jumps with the slow pointer. And you can see this is the first position that they intersected at. So this was the intersection of the 2 pointers, right? This was the first intersection. So that's the first phase of this algorithm. First, we find the first position that they intersect at. Then we take our slow pointer, leave it here. So our slow pointer is going to be here, right? And then we're going to be done with the fast pointer. We're going to take a second slow pointer and put it right at the beginning of the array. And each of these slow pointers, we're going to keep shifting them by 1 until they intersect 1 more time. So this slow pointer is going to be shifted by 1. This slow pointer is also going to be shifted by 1. Hey, we just found out that they intersected, right? And this second point of intersection is always going to be the result. It's not intuitive at all why this is the case yet, but let me explain that. But now you know the algorithm. If all you wanted to do was memorize it, that's literally it. Now you can code it up. That's why I don't like this problem, because it's simple if you've solved it before. So this algorithm relies on the fact that the intersection point, like the first intersection between the 2 pointers, the distance between this point and the beginning of the cycle, which in this case is 1, right, is always going to be the same as the starting point distance from the cycle, the start of the cycle. That's also 1, right? Since we know that's the case, that's how we can take 2 slow pointers, start one here, and then keep shifting until they intersect, then we get the result. But why is it the case that the distance between this is the same as the distance between this? Looking at this bigger example, why is it that the distance between the start and to the start of the cycle is always going to be the same between the intersection and the start of the cycle? Why is that the case? Well, let's just draw out a few distances. Let's say the distance, this is p, right? Basically, p is the number of previous nodes we have before the actual start of the cycle. And let's just say, you know, arbitrarily, this is the intersection point between the 2 points, right? And we don't know that this is going to be the same, so let's just label it x for now. Let's not label it p, because we don't know for sure that it's going to be the same. Let's label it x. This is our unknown. And then the remaining portion of the cycle is going to be c, which is the length of the cycle, right? In this case, it's 5, minus x, right? Because the total cycle is 5, which is c, and this x portion makes up the remaining portion of the cycle. That's why this part is c minus x. So we know that the slow pointer is going to start at the beginning, it's going to traverse this p portion, and then it's going to traverse this c minus x portion, and it's going to land at the intersection point, right? Now we know that the fast pointer is going to do more than that. It's going to, of course, do this p portion once, then it's going to do a complete loop, right? Because remember, the fast pointer is going to outloop the slow pointer, and it's going to overlap the slow pointer, so it's going to have to complete a at least one full loop, and then once it does a full loop, it's going to be back here, and then it's going to traverse this c minus x portion to get to the intersection point, right? We don't know where the intersection is. Obviously, I drew it over here, but it could be anywhere. So let's write that mathematical equation out. So we know that 2 times the number of iterations the slow pointer does is equal to the number of iterations the fast pointer does, right? How many spaces it moves versus how many spaces the slow pointer moves. Of course, the fast one is twice as fast. That's why we have to multiply the slow one by 2 to make it equal to this one. And how many iterations did we say that the fast one does? It's going to do p plus cx, right, to get to this position. And then it's going to do another complete cycle starting from here to get back to this position, right? So it's the fast pointer is going to be p plus c minus x plus c again. So more simplified, it's going to be p plus 2c minus x. The slow pointer is just going to do p, and then it's just going to do c minus x. So we'll have a 2 on the outside, p plus c minus x. So I'm going to take this equation and simplify it over here to the right. So once we simplify it a little bit, we're going to get 2p plus 2c minus 2x, which is equal to p plus 2c minus x. And then this is the part where you can start doing a little bit of algebra. So we can cross out the 2c from both sides of the equation. We can cross out 1x from each side of the equation. And we can cross out 1p from each side of the equation. Once we do that algebra, we're left with the equation, and sorry that it's getting a little bit messy, we're left with a single p and a single negative x. So we get p minus x is equal to, notice how we crossed out everything on the right side. So we got p minus x is equal to 0. When we rearrange that, we get p is equal to 0. What did we just prove? We just proved that the pre-portion of the cycle is always equal to this, right? So that's how we know once we have a pointer over here, then we can set another slow pointer over here, keep iterating them by 1, and for sure when they meet, they're going to meet at the start of the cycle. They're always going to meet at this position. So I hope this explains a little bit of the intuition and a little bit of how, this is very rigorous. This is a proof. This is always going to work. And now you know why it's always going to work, but the code is actually really simple. Now, one last thing I didn't mention before we dive into the code is that notice how this pre-portion could be really long. It could be even longer than the entire length of the cycle. So how would that update our math? Would our math still work out in that case? And I didn't include this in the math because I don't want to overcomplicate it too much, but yes, the math would work. Instead of having 2c over here, we would have an n over here, and the math would end up still working out. Basically, we would always start back at the beginning here. We'd traverse this many nodes, and then from here, basically, instead of just traveling this small distance, it could be possible that we would have to do multiple loops, because if this distance was really long, longer than the length of this loop, we would have to do multiple loops. But after all of that, the remainder would still be this portion left. So we would still end up getting to this position, the start of the loop. Okay, now we can finally get into the code. So remember, we're going to be starting at phase 1 of this algorithm. We're going to have 2 pointers, fast and slow. They're always going to start at 0, remember, because we know 0 is not a part of the cycle. That's for sure. And we're going to keep iterating through these loops. I think there's an easier way to write this code, but I'm lazy, so just while true.
Okay, let's try. Whoops. No head. It's an array. So while true, what do we want to do? Slow. Equals nums. What could be like slow plus 1? Could be slow plus 1. Plus 2.
True. We're going to, and we start out with while true because we want to keep going until they intersect, but notice how they already intersect at the beginning. So we're going to update slow. So basically slow is going to be set to whatever it points at. So nums of slow, right? And then fast is going to be the opposite, or the same thing, nums of fast. But remember, we're advancing fast twice, and so we can just do this. And of course, fast and slow are always going to be in bounds, right? They're never going to point out of bounds. We know that for sure based on the restrictions that we're given. And if slow is equal to fast, that's when we can break out of the loop. If they're not equal, then we're not going to break. This is basically a do while loop, but I don't think you can do that in Python. So once we've done this, that's how we know, okay, fast and slow intersect.
I don't understand this though. Nums of slow. So first it's like it'd be, if you're using this array, it'd be 1, and then fast, nums of fast is going to be 0. So 1, and then fast of 0. What's that going to be?
Affected here. So now we're going to create a second slow pointer, slow 2. We're going to set it to the beginning, right, back at index 0. And now we're going to keep incrementing this slow pointer and the first slow pointer until they intersect. So this is phase 2 of the algorithm. While true, advance the slow pointer by 1, and advance the second slow pointer by 1 as well. Notice how trivial this code is. The hard part is just figuring it out. So, and we're going to keep going until they intersect. So if these were equal, then we can break out of this loop and then return the slow pointer, right? We can return either of them, slow 1 or slow 2. Index that they're at, right? Slow 1, and slow 2 are always an index, and the index that they're at is the duplicate number because we have multiple values pointing to the same value. That's the duplicate. We can actually take this and return it here. So I'm just going to go ahead and do that, and this is the entire solution. Okay, I don't know what I was thinking. I don't know why I put fast on the outside. This is nums of fast, which is a number, which is a different index, and then we're going to use that same index again in the nums array. That's how we're basically advancing fast by 2. We could obviously write it in different lines of code, but I'm just going to leave it as it is just because it's a little bit neater.
Yes. Let's see. So nums of slow, and then fast. Nums of fast is going to be 0. Wait, nums of fast 0, so that points to 1, and then nums of 1 points to, so now it's 3. So if I did nums of 3, give me 2. So if slow fast break, so let's just go over it. So slow, so nums of 0 is 1. So now 1, nums of 1 is 3. Nums of 3 is 0, 1, 2, 3 is 2. Nums of 2 is 0, 1, 2, 4. Nums of 4 is 0, 1, 2, 3, 4 is 2. Nums of 2 is 0, 1, 2, 4. Nums of 4, 0, 1, 2, 3, 4. Okay, now we're gonna have a cycle. Okay, so fast. Because we're doing it 2 times, nums of 0 is 1, and then nums of 1 is 3. Okay, so nums of 3, 0, 1, 2, 3 is 2. Nums of 2, 0, 1, 2 is 4. Nums 4, 0, 1, 2, 3, 4 is 2. 4. Wait, what? Nums of wait, nums, okay, nums of fast is 0, it's 1, and then nums of 1 is 3, right? It's 3, and then nums 3, 0, 1, 2, 3 is 2, and then it's 4. So ends at 4. So they meet at 4. Okay, so they meet at 4. So index, they both equal 4. Slow 2. So this is, and then we repeat it again. Slow 2 equals nums of slow 2. Slow equals slow nums of slow. I mean, this is just going to be the same thing, right? 1, 3, 2. 1, 3, 2, 4. 2 should be enough. So slow ends slow is going to be 0, 1, 4 is 2. 2.
And also, I don't really know what I'm thinking, but the second slow pointer also needs to be advanced. I don't know why I called it slow 1, but that is the entire code. And then once they finally meet, we are going to be returning that index. And as you can see, the solution does work. It's a linear time solution. We definitely didn't need to use any extra space. We didn't need to modify the input array.
Time complexity O of n since pigeon. What the fuck? Bro. Okay. Kind of got this, but this is think about why it's it where it is hair it won't seem like it since we're array. Okay. I got really excited answering this question. Yo, this looks fried as fuck. LRU cache initializes the LRU cache with positive size capacity. Return the value of the key if the key exists. Whoa, is another tortoise in the hair problem? Okay, this is fucked. Just gonna watch the solution for this. Holy shit. This is 146? Yes.
Hey everyone, welcome back, and let's write some more neat code today. Let's take a look at a really popular interview question, LRU cache. It's even asked by Twitch TV. It's one of their most popular interview questions. And also, don't forget to like the video. It supports the channel a lot. So this is definitely more of a design problem than an actual algorithms problem. So we have some kind of cache that's going to store values. It has a capacity, so it's fixed size. And we want to be able to get values from this cache based on a key value. If that key value exists, then we'll return the value that it corresponds to. If it doesn't exist, the default value we want to return is -1. And if we're getting values, we also need to be able to put values into the cache. We're putting them in based on key value pairs. And there's a lot of edge cases, and they explain a bit of them to us. If the key already exists in the cache, then we just want to update the value. If it doesn't already exist, then we're inserting it for the first time, so we can put that key value pair into the cache. And remember, this does have a fixed size capacity, so if we ever exceed the capacity, then we have to evict the least recently used. So that's why this is called the LRU cache problem. And it also makes sense, right? If there's a key that we're not really using, then that's the one that we're going to take out of the cache. And this is actually pretty similar to how browsers work. So for example, if you're using Chrome and web browsers have caches, if there are values that we're not really using in that cache, then of course we can remove them. Let's also try to solve this the most efficient way, which is each of these operations, get and put, are going to be constant time operations. And it's going to be kind of tricky, but it's definitely possible. So let's just look at the first example. So the input is 2. So that's something that we need to kind of remember, right? The capacity is 2 in this case. And the next operation is put. So we're putting a pair of 1, 1, key 1, value 1. And we're going to keep these kind of in order, right? Because we put, right, the capacity is 2 possible. So let's just look at the first example. So the input is 2. So that's something that we need to kind of remember, right? The capacity is 2 in this case. And the next operation is put. So we're putting a pair of 1, 1, key 1, value 1. And we're going to keep these kind of in order, right? Because we want to remove the least recently used. So we got to kind of remember in what order are we adding these values in. The next one is another put operation, and we're putting 2, 2. Of course, for these first 3 operations, we're not really returning anything, so the output is going to be null. So next, we're actually doing a get operation, and we want to get the value that has a key of 1. And remember, we're trying to do this as fast as possible. We're trying to do each operation in constant time. So how can we know instantly what the value is when the key is 1? Well, the easiest way to do that would be with a hash map, right? So we're going to use a hash map to instantly look up the value of every key. We can, of course, do this in constant time, and we know that the size of this hash map doesn't need to exceed our capacity, so we can have only 2 values here, right? So for the key value, we can use the same value that we use for each of our nodes. And for the value, we could also do the same thing. We could use the same value that we use in our nodes, but I'm going to show you why it's going to be a little bit better for us instead to have the value be a pointer to the node itself. And we can do the same thing with the second node that we inserted as well. So for key value 2, we're going to also do the same thing. We could use the same value that we use in our nodes, but I'm going to show you why it's going to be a little bit better for us instead to have the value be a pointer to the node itself. And we can do the same thing with the second node that we inserted as well. So for key value 2, we're going to point at this node. So now finally, when we call this get and we ask for the key 1, we're going to return the value 1 that's over here, which is exactly what the output tells us is correct. So since we just used the get operation to get this one, we went to our key, then we found this value, and then we returned that value. That makes this the most recently used value, and this is the least recently used value now. So I'm going to keep track of the most recent and least recent by having a left and right pointers, right? So this left side is going to be the least recently used, and the right over here is going to be the most recent. So therefore, we're basically going to be swapping these two nodes, right? And so this portion of the problem is starting to keep the ordering of these. It looks like we're going to need a linked list. And not only a linked list, but a double linked list. Because remember, we can easily look up where these values are, but if we want to also reorder them quickly by for example, every time we use a get operation, we want to take this value and then move it over here because it was the most recent. And so now we're going to reorder the two nodes. So now this is the least recently used and this is the most recently used. And since this is a doubly linked list, we need the pointers to be connected. Of course, the hash map won't really need to be updated because these are pointers. They're already going to be pointing to the correct ones, and I'm not going to show that. And now we can get to the most interesting operation, the third put. So we're putting a third value, key value, 3, and since 3 is greater than our capacity of 2, then we're going to have to remove the least recently used value, and convenient for us, we know exactly what that value is. So first, we're going to end up updating these pointers to make the least recently used 1 and get rid of this. And of course, we want to replace that 2 since we know it's the least recently used. We want to replace it with the new key 3. And now we also want to update that pointer. We want it to point at the new node. And since the new node 3 is the most recent, we're going to put it over here. 3. And the pointer is going to point here. This pointer is going to point here. And there's going to be a double link between them. So this is basically the main idea. We're going to keep track of a capacity. We're going to have a double linked list. We're going to have a hash map where the key of the hash map is going to be the same key that we get from the input, and the value is going to be a pointer to the nodes. And each node is going to look something like this. And it's going to have 2 pointers, remember? So it's going to have a previous pointer and a next pointer. And don't forget about this right and this left. These are also going to be nodes because we want to have pointers. We want to be able to instantly know what's the least recently used and what's the most recently used. So these are going to be dummy nodes pretty much. So getting into the code, remember we're going to need a node. So before we even write this LRU cache class, let's make another class for that node that we're going to use. And remember, each node is going to have a key value pair. So we're going to get those. We're going to initialize those. And we're also going to have 2 pointers, one for the previous node and one for the next node. And they're both going to initially be set to null. Now when we actually get into the LRU class, we know that the capacity needs to be stored because we want to know if we ever go over that capacity. We also need a hash map, and I'm going to call that our cache. And remember, this is going to map the key to nodes. And before we
Bruh. My brain. I don't think I need timer. I think as long as I finish this problem later, it's going to be fine. But holy.
have any values in our cache, we want to have a couple dummy pointers, a couple dummy nodes, which tell us what are the most recent and least recent values that we added. So we can just initialize these to 0 for the default values, so 0, 0. And initially we want these nodes to be connected to each other, because if we're putting a new node, we want to put it in the middle between left and right. And we can do that with some pointer stuff. So left.next is going to be right, and right.previous is going to be left. And remember, left is going to help us find the least recently used, and right is going to be most recent. So now let's start with our get function, because it's mostly straightforward. If the key exists, so if the key is in our cache, then we can return that value, right? So we can return self.cache of key. Now this tells us the node, remember, because each key is mapped to a node. So to get the value, we can just do .val. And of course, if it doesn't exist, they wanted us to just return -1. Now the only thing we're forgetting with this get is that every time we get a value, we want to update it to the most recent. So to help us with this part, I'm actually going to write a couple helper functions. So I'm going to write a remove and insert helper function. And these helper functions are going to be applied to our linked list. So we're going to pass in the node that we want to remove from our doubly linked list. And I'm also going to write a function to insert into our linked list. And when we insert, we're going to insert at right. And the remove is just going to remove from the list. So these are basically going to be pointer functions. We're going to be manipulating some pointers from our left, from our right, and doing some stuff. So I'm not even going to worry about that. All I know is that we have a helper function that can remove any node from our list, and a helper function that can insert any node at the rightmost position of our linked list. So since we're getting, what we want to do to our list is take this node, self.cache of key, and remove it from our list. And after we remove it, then we want to reinsert it at the rightmost position. So we can just do self. And looking at this, get isn't so bad as long as we fill out these two helper functions for us. So now when we actually look at our put function, let's remember that if we have a key that's already in our cache, that means that a node already exists in our list with that same key value. So before we can insert this new key value pair,
Don't lie, this video is kind of missing. How are you? I'm doing LRU.
Hello guys, welcome back to TechDose, and in this video we will see how to implement the LRU cache algorithm, that is the least recently used cache algorithm. So let us first understand what is least recently used algorithm. Let us say our cache window size in our computer is 3. That is at a given time this cache. Now in order to move to both 3, and this will be pointing like this. So everything
What's up everyone? Sam here from bytebytebite.com, and in this video I'm going to show you exactly how to implement an LRU cache. So it's the least recently used cache, and this is a very common problem in a lot of coding interviews. So we're going to dig into it right after the intro. And if you haven't already, make sure that you hit that subscribe button and the bell icon so that you get notified every week when we release new videos.
Alright, in this video we're going to talk about how to implement an LRU cache. And this is a pretty common problem, so it's definitely a good one for you to understand how to solve this and also understand how to work through, and it's a good demonstration of how to use the BUD optimization as well. So with this problem, basically, the structure is a little bit different because we're implementing an LRU cache like class, and so really what we're doing is we're implementing these two functions. So it changes our approach a little bit in the sense that we don't really have to be, we don't have to be super conscientious about like defining the functions ahead of time. It also actually, on leetcode at least, it tells us what the runtime that we're expecting for this problem is, and so that makes it a lot easier as well. It's telling us that we want to ideally do both of these operations in O of 1 time, which means that we want to do them in constant time. And so let's look at how we can approach this problem. So with an LRU cache, just to make sure that we're all on the same page here, the basic idea is that we're going to implement a cache. It's going to be, a cache of some set size, and then what we're going to do is when the cache is full, we're going to evict the least recently accessed item in the cache. And so, we might have a cache that had values in it, and I guess the one thing we do want to make sure that we're clear on here is what the types of the key and value are. So, in this case, get is going to return an int, and key and value are both going to be integers as well, just to keep things simple. And so maybe we put in our cache 1, 2, 3, 4, 5, 6, and then now let's say that we wanted to add another item. Well, our cache is full, and if we put the 1 in first, then that means that the 1 is going to get evicted so that we can put 7 in, and then the 2 would get evicted to put 8 in, etc., etc. And so how can we implement this? Well, we sort of need to do two things, right? Like first, we need to keep track of what the order is of the elements. And so we could do this in a couple different ways. Like we could say, for example, let's keep an actual, set of when like a timestamp of when they were most recently accessed. Or like, there are a lot of things we can do like that, but we want to make sure that we're not overcomplicating it. And so, this is a perfect example where I think it's easy with the brute force solution to start getting really complicated. But let's back up and think, simply, how can we just keep track of what is the next item, or what is the item that we need to evict? And so a really easy way to do that is just to keep the items in order from most recently accessed to least recently accessed, right? Or least recently accessed to most recently accessed, because it doesn't matter what the actual time that the element was accessed at, it just matters the relative times that we access the different elements. And so what that leads me to immediately thinking is, what if we stored our elements in some sort of sorted data structure, right? Like maybe we could store them in a heap, maybe we could store them in a list, maybe we could store them in even an array potentially. But I think the easiest thing here, because we're going to potentially what we want to realize is that we're potentially going to be updating this order over time. And so it seems like the easiest option here is just going to be a linked list, right? Because the linked list of the items will be in some fixed order, and then if we want to, when we access the item, all we have to do is pick it out and move it to the front of the list. And so let's look at like what this would look like. So we would have a list like this, and so we might have like 1, 2, 3, 4, and then let's say that we had get 2, then what would happen is we would remove this one and put it at the beginning. So we'd have 2, and then 1, and then 3, and then 4. And every time we get an item, all we have to do is we have to find it in the list and update it. Or if we, if we try and put another item, it's going to go at the front. So 5 would go here, and then we would just evict the last element of the list, right? So we would just remove the very last element. And so functionally, that's a really easy way for us to keep track of just like what is the order of like when they've been accessed. But the problem with this obviously is that this is not going to take O of 1 time, right? It'll take O of n time for us. So like let's look at these individually. So first, if we want to get something, it's going to take us potentially O of n time because we have to iterate over the whole thing to even find if it's in the cache or not, right? And then to put it, then that could take constant time depending on the size of the cache. But if we need to evict this last element in the cache, then that's also going to take O of n time because we need to iterate all the way through to the end to access that value. And so the question is, how can we do this more efficiently? Like, can we do it with a linked list and also do it more efficiently? And the answer is, of course, yes, because we know that we're going for this specific time complexity for both. And so what is the issue here? If we look at our BUD optimization, the issue is really that every time we're doing something, we're iterating over the whole list. And so we're doing all of this work every time. And the question is there a way that we could avoid having to iterate over this list? So let's say that I had a linked list, and I have the values in it. And basically what I want to know is I want to be able to tell without having to iterate over the entire list if an element is in the list, and if so, where it is, right? And so let's say that I have, get 3, and obviously I'm not including the values here. I'm just putting the keys because, the value would be stored in this list somewhere, and we can just sort of ignore that.
Hi everyone. So
The advantage of the doubly linked list as well is that when it's to the beginning and the end fairly frequently. And hopefully you're seeing as well how, this is slightly different than some of the other problems we've done, but it's the same basic idea.
So we're going to retrieve this item, and then this is the video. If you like this video, hit the like button, subscribe to the channel.
Hello everyone, welcome to my third day LeetCode challenge. I'll be solving the LRU cache question. And so the question is, design and implement a data structure for the least recently used LRU cache. It should support the following operations: get and put. So get key, get the value, which will always be positive, of the key if it already exists in the cache, otherwise return -1. So it's just a typical, get method for like a dictionary. And a put, set or insert the value if the key is not already present. All right. When the cache has reached its capacity, it should invalidate the least recently used item before inserting a new item. So basically, if we're putting in a key, that would be the most recently used one. If we have gotten it as well, that would also be recently used. So it's whatever key that's not either gotten put in or gotten get. The cache is initialized with a positive capacity, got it. And there's follow-up. Could you do both operations in a one-time complexity? So we'll ignore that for now. I don't know if I can accomplish that. Here's the LRU cache. Like, you initialize it with a capacity of 2, so now it's going to only be able to hold 2 keys, right? So it's going to put key 1 with a value of 1, put key 2, value of 2. We're going to get key 1, which is going to return a value of 1. If we put key value or key 3 with a value of 3, that's going to evict key 2, right? Because we've already gotten 1. So the least recently used one would be 2. And if we look for 2, that's going to return -1 because it doesn't exist, so on and so forth. So the first thoughts I had when I saw this question was maybe we can do this with like a heap of some sort. But as I tried to implement that solution, I quickly realized a heap's not going to work, because even though you could conceive of a way to push, let's say, the least recently...
What the heck is a heap?
used key to the top of the heap. Whenever you put in a key, the problem is if you're going to get the key, you have to sequentially look through the whole heap again. So that just didn't work. And ultimately, I ended up using a kind of hacky solution. Imagine that, like, what we need to have if we had like a dictionary of, ignore the values for now, let's say we just had something like that. This was our LRU cache, and we want to get 1. Okay, that's going to get put to the back of the list, right? Because that's been recently used. And 2 is now the least recently used. So if we added like a new key, like 4, that's should push off 2. So you can imagine, like, this kind of brings in a problem because a dictionary doesn't ever keep order in mind, right? So we'd have to use some sort of combination of like a dictionary in order to keep the get method of big old complexity of 1. And we need to keep track of this queue. We need to keep track of the order. So the way that I eventually did it was I decided to use an order dictionary. There's a collections library, I think it was like that, and in the collections library, there's something called an ordered dict. And that's just basically a dictionary that keeps track of the order, and you're able to move keys like to the back of the order as well. So that's going to do quite nicely for this LRU cache. Let's start with initialization. So we've been given the capacity, and that'll just be the capacity that's entered. And we want to also have this actual object that we're going to use, and I'm going to call this key value. And I think it was like this. So it's basically a dictionary. It works the same way. It's not as efficient for some reason, but you know what? That's not important for now. Just
Okay, I'm gonna go eat something and continue on with this.